My name is Edwin Gasparaj. I'm the founder and principal consultant at Six Sigma. We are a digital manufacturing company. We develop complex machining solutions by integrating CAD, CAM, and CNC systems. Airfoil is a great example of such integrations. Even though this airfoil looks really smooth, during engineering design, various manipulations of these surfaces introduce all kinds of surface imperfections and curvature reversals and other artifacts that make it extremely difficult to machine these parts and produce really a smooth surface on the CNC machine. This, combined with tight tolerance requirements on these parts, make it an even bigger challenge. Today, we are going to take a look at 3 different machining scenarios and how we are going to use CAD, CAM, and CNC systems and the integration of these 3 systems to solve those problems. In the first example, you will see how Sinumerik 840D's path and axis smoothing options, along with toolpath options from NXCAM, produce smooth and accurate surface finish. In the second example, we will demonstrate a unique part positioning method. This uses 5-axis probing in NXCAM and EES from Siemens 840D. In the last example, we will demonstrate an adaptive machining toolpath. This uses probing results from a Bloom Digilog scanning probe. Let's just start with a simple airfoil milling toolpath. Small wiggles in airfoil surfaces often cause tiny variations in rotary axes of the CNC machine. Here we are looking at the curvature map of one of these cross-sections of this airfoil. Even if the rotary axes of the machine can respond quickly, the linear axes have to catch up and be in sync. Navigating around the tight leading and trailing edges always requires a high dynamic response from various machine tool axes. Siemens path smoothing options in cycle 832 and Grobe's customization of it for its machine kinematic and dynamic behavior produces excellent surface finish right out of the box. There are instances, however, where these axis reversals are so hard to predict and identify. To circumvent this problem, Siemens provides an onboard trace diagnostics for each axis, and we can monitor a variety of machine parameters using this trace function. In this example of the tool axis trace, the top curve shows the main rotary axis of the table. Whenever you see this graph going up, the table is rotating clockwise. If you see it going down, the table rotates counterclockwise. Here, we are machining the concave side of the blade. As we get closer to the leading edge, there is a small area where the axis reverses to a counterclockwise direction before it proceeds with its clockwise movement. In this small momentary area, because of the axis reversal, the rest of the linear axes have to quickly catch up. If they do not, we end up with surface marks that we are going to see as a photograph later. We were able to solve this issue by fine-tuning the tool axis in this area. NXCAM has a vast array of tool axis and projection options. You can pretty much get any toolpath and tool axis you can imagine with all these options. This is the toolpath trace after the tool axis reversal was corrected. Here you can see that the main rotary axis always makes a clockwise direction. In the previous example, before the correction, at this area, the graph dipped and then picked up. Here you see that we were able to correct it and continue with the positive clockwise direction of the axis, which produces a much better result. The result is a smooth surface that requires no further manual polishing. The tolerance of the part is maintained well under 1/1000th of an inch. Here's a comparison before and after. The image on the left shows surface imperfections caused by axis reversals. The image in the middle shows what it looks like after hours of manual benching. The image on the right shows what we were able to get after the axis correction. In the second example, we are going to show how we use 5-axis probing features in NXCAM. We also use EES, the externally executable source feature in Siemens 840D. This allows us to probe the part, push the results to the PCU, run our custom math routines, and bring back the alignment to the controller. Here we have a part that has already been finished machined. This part does not have any planar or cylindrical surfaces for us to easily indicate and locate. This part would typically require a complex fixture to locate the 6-point datum nest of the part. Instead, we are going to place this part in a simple vise, use our Bloom Digilog scanning probe. This allows us to probe, push the probing results to the PCU on the controller, where we run our custom software. We compute the new alignment and mathematically assign the alignment to the fixture offset of this part. We are finding the initial location of this part, and we will soon see how far the part is off target on the screen. As you can see, some of the points on the part are off by more than 20 thousandths and 10 thousandths here, 14 thousandths here, and 57 thousandths here. In the next few iterations of probing, after we make the correction, you will see these numbers reduced down to less than a few microns. So we took the probe results and we sent it to the PCU unit while the PCU is processing the machine weights. When the results are calculated, the offsets are pushed back to the control, and we are going to run the probe one more time to find out how close the values are. As you can see here, look at these numbers, 0.00007 and 0.000005 inches. These are less than a micron. We were able to locate the part and tell the system exactly where the part is. To prove that we have located the part exactly, we are going to try removing just 0.5 thousandths of an inch from the part. That's about 12 microns. So we have color-coded the part. Because we were able to perfectly align the part, you can see that it is removing the intended amount of material on both the convex and concave side of the airfoil. As you can see, because of the perfect alignment in all 6 degrees of freedom, we are able to remove the intended amount of material, not just near the tip, but all the way through to the platform. As you can see, being able to exactly locate the part has many applications. Airfoil repair, being able to correct coatings, being able to machine the datum surfaces of ECM'd, cast, or forged parts. This is also very useful in centering 3D printed parts inside the intended volume and machining datum surfaces. In our final example, we are going to show you a closed-loop adaptive machining toolpath. We will also use Bloom's Digilog part scanning probe in this example. We have taken the part out, put it back in the vise. I'm going to hit it with a mallet to mimic part-to-part variations. We are going to then scan the part and try to refinish just the top few microns of the part. Here, we are using the Bloom Digilog scanning probe to scan around the airfoil and find the deviations. We will use those deviations and run an adaptive machining toolpath next. Here is our adapter toolpath. We have taken the results from the Bloom scanning probe, used the probing results to morph the toolpath, and we are running the morph toolpath here. Each single line that you see here highlighted on the screen indicates one go-to line. Some of these lines contain over 700 characters just to indicate X, Y, Z, and the axis position at each individual point. So on top of a solid machine tool like the Grove 350, by bringing together the CAM, CNC systems, and post-processor, we are able to maintain very tight tolerances even on large parts. Typically, we maintain less than a 1/10 tolerance on a part that's about a few inches long, and less than 1/1000th of an inch tolerance even on parts about 3 feet long. If you have been around CNC machines, it may seem like nothing has changed in the past 20 years, but if you look behind the scenes, the amount of data being collected and the speed at which this data is processed behind the scenes has significantly improved. Controllers like 840D have taken full advantage of this computing power and have brought us an open architecture which allows us to post-process complex toolpaths like these and produce excellent surface finish and tightly toleranced parts. And finally, it is not just sufficient to buy expensive machines. It takes a lot of effort to bring together the complexities of the CAM system and what's available in the CNC control to produce these fine parts. Thank you.